and that, I'm really, really excited to start with the first keynote of the day. And I'm really, really honored that Shai Shalev from Mobileye made it here. And I want to share that this is one of the companies that I've been most inspired for the longest time. Like when the moment I was like younger, I always thought that like autonomous driving is the future. And I mean, I've been like completely wrong. I always thought it's like 3 to 5 years in the future. I thought like, I mean, I actually like made a bet in 2015 with my CEO and boss at that time that by 2020 there would be 100,000 autonomous vehicles on the road. And I mean, we have now 2024 and there's nowhere near 100,000 autonomous vehicles on the road. And the reason why I'm telling this story is Mobileye was one of the companies that had a clear path and vision on how to make autonomous happen by going towards like advanced driver assistance systems. They have like said, look, this technology is going to happen, it's going to change many, many lives, but on the way to autonomous, basically, you will need to deploy systems that generate value. Right? Like, and now their systems are saving thousands of lives every year because they developed like advanced safety systems, like braking in a car before you hit a pedestrian, like keeping you in the lane in curves and stuff like that. So they're the only autonomous company that has shipped tens of millions of systems. And that is like really something that I always take inspiration from, that we need build technology that's not like super cool because we all love building cool stuff as geeks, but to create value as soon as you can. And that's why I'm really, really honored that we have Shai Shalev-Shwartz, the Chief Technology Officer of Mobileye, where he heads the development of software and algorithms for advanced driving assistance systems, as well as the future of autonomous systems and driving solutions. He's also a professor at the Rachel and Selim Benin School of Computer Science and Engineering at the Hebrew University of Jerusalem. So he really is a deep tech expert and knows what he's talking about. He's been instrumental developing the science behind the responsible safety systems and road experience management maps that Mobileye has been building. And he has been pivotal to ensure the vision for zero casualties from car accidents. He's a pioneer in machine learning, way before it was cool, like a decade ago, when the latest Gen AI craze was nowhere near there. He's co-authored like some of the textbooks that some of you might have read, Understanding Machine Learning from Theory to Algorithms. He's published like more than 100 research papers. He's won the prestigious Michael Bruner Award in 2020. So I couldn't be more honored than having Shai open this conference. Please give him a big round of applause. Thank you so much, Shai, for coming all the way here.
So I'm going to talk about personal journey around the artificial intelligence that started around 25 years ago. Tell you a little bit about what's going on in this field from my own perspective. And I think that the amazing thing is that we are living in a wonderful time where we see revolutions in artificial intelligence, and the pace of this revolution is really amazing. So let's go over 6 AI revolutions that happened in the last 20 years or so, where the last 4 of them happened in the last 4 or 5 years. So the pace is really accelerating. Starting before the revolutions. So 25 years ago, I worked at a small startup in Jerusalem, designing AI computer vision systems for detecting ellipses in images. This is for ultrasound, detecting the circumference of the head of a fetus and stuff like that. And everything was classical AI computer, no machine learning. 2000. 10 years later, I joined Mobileye. And everything was shifted in 10 years from expert systems to learning algorithms. Back then, the learning algorithms that we have been using were support vector machines and boosting algorithms like AdaBoost on hand-tuned features. So you were going and the expert was designing features for the domain, and the machine learning algorithms combine these features based on data into something that give good predictions. It took 10 years to shift the industry from everything is crafted by code to only the features are crafted by code, and algorithms, machine learning algorithms, are adjusting weights. And around 2014, I wrote a book about the theory of machine learning, and I thought we had a pretty good understanding of the underlying theory of machine learning. I was completely wrong. So deep learning came around 2012. Of course, everything was before, but the real one paper that made a revolution is a Krzyzewski, Sutskever, and Hinton paper on using convolutional neural network for making a huge jump in the ImageNet dataset. And the difference between deep learning and what we used before was that deep learning said no more hand-tuned features, just give me the raw pixels, and the neural network will learn by itself also the features, how to combine them, and how to make predictions out of it. And we were at Mobileye early adopters of this technology. 1 year later, we were already having convolutional neural network running on our datasets. And it was deployed 2 years later, 2014, as a first generation of Tesla Autopilot. It was based on a Mobileye system that predicted lanes and cars, etc., based on deep learning algorithm. So this is the nature of a revolution where you have a strong technology, and in 2 years, you are making a big jump into something much stronger. So let's move a few years forward, 2019. Again, things started before it, but in 2019, I joined a startup called AI21. And we were working on rephrasing. So if you write some email or whatever you want to write, and the system can suggest rephrasing of better phrasing of what you want to tell. And here, it is very complicated to rely on supervised learning, which was the essence of what we have been using in convolutional neural networks and in deep learning pre the self-supervised revolution. So basically, how did we use deep learning? You needed to have a company. You needed to have enough money. You needed to have humans in the loop that labels images. For example, we had a big team that just sat in front of computers, looked at videos of our cameras driving, and put rectangles around cars. And this was fed later to the deep learning algorithm in order to teach it what is a car. But the self-supervised foundation models brought a revolution that we no longer rely on supervised learning. We no longer tell the computer exactly what we want it to do. Okay? We just give it data and tell him, go figure out. Okay? Understand. And this is amazing because today it looks very natural to all of you, probably, because you got used to large language models and the miracles that they are doing, but 10 years ago, it looked like science fiction, completely. So how does it work? Basically, we call it self-supervision. Okay, this is how large language models are being trained. So basically, we want to learn a network that minimizes the log loss. The log loss is what is a logarithmic of the probability of the next token, think about it as the next word in some document, given the previous words in the document. So naturally, you don't need any labels. Basically, you are using the future of the document as self-supervising itself. And the idea here is that this gives a model of the internet, a model of how documents are distributed in the internet. Okay, that's nice. So I know how documents are in the internet, but I need to do something useful out of it. So here comes in-context learning. So we are giving 0 shot or 1 shot or few shot. We're just explaining somehow to this model what we want it to do. And then the model from the explanation understand what we really, in this specific task, want it to do, and it performs it. We call it in-context learning. So this was the third revolution. We're talking now about 2019, around 5 years ago. But it didn't end, because then came the consolidation revolution. What I'm talking about. So again, if you look 20 years backward, then there used to be computer vision experts, natural language processing experts, speech processing experts. Each of these experts had their own conferences. They couldn't speak with each other, okay? They used different tools, completely different tools, and everyone lived in his own world. Then came the consolidation revolution. The consolidation revolution means that today, natural language processing experts, computer vision, speech processing experts can all understand each other. They basically all doing the same, okay, or very similar things. Video processing, video generation, image understanding, all are using the same set of tools. It's deep learning, and actually even almost the same architecture of the deep networks. So all of this is very nice in the cyber world. So if we want to do things in the virtual world, then these self-supervision and understanding things are really working great. But this is just one learning paradigm. We call it the learning from data. So basically you see data, and you need to figure out something out of this data. But if you want to learn how to shave, it's not a good idea to just watch YouTube videos and learn how to shave. You need to try it out, okay? And this is a second learning paradigm, which is called learning from experience. It's not the data, you need to try it out. And after you try it out several times, then you figure things out. So this is what is required in order to go to robotics. In order for a car to behave out there in the world, or in order for a humanoid robot to walk around, it needs to learn from experience and not only from data. It cannot just passively watch data and figure out everything. The problem with learning from experience is that now we are constrained by the physical world. The physical world is slow relatively to the virtual world and is dangerous. Because if you are doing mistakes in the physical world, then it's dangerous. It's your robot falls down and broken, or worse, think about a car that makes a mistake. Okay? So how can we tackle it? How can we learn efficiently things that are relevant to the real world? One idea is, let's use simulations. This is not a new idea, it's a very old idea. But the problem with simulation is that it doesn't really reflect reality perfectly. So we are suffering from distribution drift. We train something on a simulator, but why should it behave normally on the real world? It's a slightly different distribution, and we might suffer from it just doesn't work on the real world. So sim to real, simulation to reality, is a set of tools in which we are learning from simulations and we apply it in the real world. So all of these 5 revolutions brought us to say that now it's the right time to talk about humanoid robots. So together with my colleague Amnon Shashua, the CEO of Mobileye, we founded a company called Menti Robotics that builds humanoid robots. So let's see a short video about what it can do.
would you like me to do?
Hey Menti, please go to the table in the kitchen and wait for instructions.
Okay, I will go to the table in the kitchen.
You can see what the machine thinks, how it decomposes, understands the instructions that it got from user, the natural speech, decompose it into tasks, match it to a nerve model that understands the entire surrounding, including semantic of where is a kitchen, what is a kitchen. So the model has internal understanding where it is and where it should be. Now it thinks that it arrives to the right place.
I have arrived. What should I do now?
Please put the fruits in the container and place it on the counter behind you.
Sure thing.
So you can watch this video online on YouTube, but you see that there are so many tasks involving in this simple task. You need to figure out what the human wants you to do. You need to decompose it into steps. So if the human wants you to go to the kitchen, you need to decompose it as what is a kitchen, where it is, what do I need to do, how do I plan to go to the kitchen, what if there are obstacles on the way, etc., etc. Many, many tasks. All of them involves deep learning and machine learning and also other AI components. It wasn't possible to do it without these 5 revolutions. But it's not the end. The 6th revolution, which is maybe the holy grail of AI, is a reasoning revolution. So what do I mean by that? In classical machine learning, the goal is to generalize on unseen data. So you see data, you learn from it, but it's not enough to explain only the data you see. You need also to generalize to unseen data. So in classical machine learning, the trick is that we assume that the data that we saw during training phase and the data that we need to apply the model during testing or during prediction phase are not the same, but are coming from the same distribution. Okay, we call it IID, independently identically distributed data in the training phase. But reasoning is something else. In reasoning, you get instruction, you get few examples, and then you need to generalize out of distribution. When I ask you a hard mathematical question, it's not exactly the same things that you saw during training. You need to apply some logic in order to do reasoning. And you need to figure out things that we never saw before. Think about Newton. Okay? Newton had to invent a whole new mathematics in order to explain the physical world around. So it really requires something else out of distribution generalization. And the initial large language models were really bad at reasoning. Okay? We refer to them as knowledgeable idiots. Okay? They didn't really understand what you want. They knew many, many things, and they could repeat like a parrot. And now they are still idiots, but they are better than what they used to be. And what happened? How come we start to see reasoning emerging from large language models? They were not trained to reason. And our best guess is that it happened by mistake, similarly to many inventions in science, that we just find out them by mistake. So someone wanted to say, okay, large language models can be really, really useful for completion in coding tasks. So let's train the model a little bit about code. But what is coding? Coding is reasoning. A lot of coding is really the essence of reasoning. So once we started training models to do coding tasks, they suddenly we see an emergence of some reasoning capabilities. And how to improve it, it's a big question, and there are many, many improvements around it. One of them is chain of thoughts and program-aided large language models and neurosymbolic reasoning in which you combine both the ability of the machine to learn statistically and symbolic learning from rules. And just as an evidence, I will give you the latest generation of ChatGPT. When you ask it how much is 3,456 times 3,678. So the first generation of ChatGPT would give you, in a very, very confident manner, the wrong answer. Okay? Now what's going on behind the scenes? What OpenAI did is that they are understanding that this is a math question that should be used, should utilize a calculator. So they translate it to a short snippet of Python code. Then they run the Python code. And then they take the output of the Python code and construct a sentence out of it. So all this finished analyzing and this code is hidden. You need to click a button in order to see what's really going on behind the scenes. But using this, now they will give you the right answer in a much, much higher accuracy and consistent manner, simply because you want to combine symbolic reasoning with large language models that are performing statistical reasoning. So these are 6 revolutions, and again, 4 of them happened in the last 4 or 5 years. So where are we going from here? We see AI models that can learn in context, that can reason, and can operate in the real world. So what I think is going to happen in the coming 5 to 10 years, we will start to see a new era of machines, robots, that are taking more and more tasks from humans, can be instructed in a more flexible way to do various tasks while having out-of-distribution generalizations. Really exciting, but a little bit also alarming, okay? Because where are we going from here? Is it going to be dangerous? Are we going to be extincted? Should we be scared? So let's talk a little bit about safety of artificial intelligence. And I want to talk about it in 2 very, very different domains. One of them is limited in the context of self-driving cars, where naturally safety is a critical thing for the success of self-driving cars. The other one is a much more general concept, which is called the AI alignment problem, and it tackles the AI problem in a maybe existential way. Okay? So what do we need to do in order that AI will be aligned with human interest? It's a general question of AI safety. But I want to start with AI for safety for self-driving cars, because maybe we can learn from this specific domain about the bigger question of the general alignment problem. So Mobileye is a company that exists 25 years. It started by the idea of just placing a single camera on the windshield inside the car in order to protect the driver from dangers. So, for example, capabilities of keeping in the lane, autonomous emergency braking. The idea here is that the machine supervises what the car is doing and protect it from dangers. But then we moved into the other way around. Let's have the machine do the job of driving. and the human will be the supervisor over the machine. So ADAS is shifting from machines that supervise humans to humans that supervise machines. And the next step is that the machines will be good enough so the humans will not have to actually supervise them. So here you saw some videos of our system, which is already in production on a model which is called Zeekr in China. But you saw several cities in the world where our system is able to drive itself while the driver is still supervising the system. What is a challenge for going to the next step in which the driver doesn't have to supervise the system? I call it the AV challenge. So the real AV challenge is a combination of two things. Each individual one exists today. One is that we require a very, very sophisticated piece of technology. Okay? Many things involved in making the car drive itself. You need to fully understand the scene, understand the intentions of other drivers and pedestrians, and so on and so forth. On the other hand, the level of accuracy that is required is extremely high. It's like in aviation. So in aviation, you need a very, very high level of performance, but it's a rather simple machines relatively to what is required in autonomous driving. So the AV challenge is that we require both. And in order to tackle it, we follow a robotic methodologies in which we divide the problem into sensing, planning, and acting. Sensing or perception is understanding what's around us. It's basically understanding the present. Planning is making predictions and what would happen if type of reasoning about the future and deciding what we want to do. And acting is actual execution of the plan. So if we plan to do something, we need to move the steering wheel and accelerate or decelerate according to the plan. So what can go wrong? Everything can go wrong. Except similarly to what we know from human drivers, you can have software, hardware bugs, like a heart attack or the driver fell asleep, which is a software bug. We try to avoid it. Perception error, I didn't see something. Bad decision making, I thought I would overtake and pass before this guy. And actuation error, I just hit the wrong pedal or stuff like that. Okay? And today, in safety, we're going to focus on the driving policy part about the planning. Why is it difficult? Because it is closed loop. Perception is open loop. You can just look at offline data, it's the same. You are not affecting the environment by understanding that there is a pedestrian here or there is a car here. But when you make decisions, like driving policy decisions, your decision actually affects the environment. And you need to plan really far ahead in advance. I see that I have 10 minutes, so I will go a little bit faster on this. So what you see here is an example of how you affect reality. So the decision of the white car to push its way or to wait for the red car affects the behavior of the red car in a natural way. And this happens every time in real driving when you have on the highway a slow truck ahead and you need to prepare well in advance to overtake it, otherwise you will be stuck. Now, the point is that absolute safety is impossible because there are other idiots on the roads. All right? So in this case, the yellow car can do nothing to prevent an accident. It doesn't have any place to run away from this accident. So basically, we cannot hope for absolute safety. And then we need to really think hard on how to defining properly what is our objective, what do we want to achieve. So one way is to say, okay, you cannot be perfect, but you can be statistically better than a human driver. We don't think this is a good idea. There are many reasons why this is not a good idea. But one of them is that I don't think that society should accept lapse of judgment, okay? So if you are going to hit a little kid because you were reckless, it doesn't really comfort me that statistically we are better than human drivers. No, we shouldn't do stupid things. So our methodology for safety is following a classical method for safety, which is called assume guarantee. You make some transparent assumption on the rules of the game, and then you work hard to make sure that you're not doing anything stupid under the assumptions. And we call it responsibility-sensitive safety. And by and large, it puts a safety net on a deep network and many AI components, which can, in average, be great, but in edge cases be very, very wrong. And the nice thing about it is that we can formally guarantee, by mathematical tools, that the AV will never cause a collision, okay? And I call it the utopic guarantee. If everybody will follow the rules of the model, then there will be zero accidents, which is always a good property of a model. So the advantages of this model is that it is transparency, it is sound, it is complete, and it is efficient. It actually runs on hundreds of thousands of cars already in production on the road, in production hardware. So all of these are important property of a good model. You want transparency, usefulness, but you also want that your model will be practical, will be relevant to everyday products. And in fact, RSS is a model of ethics, is a model to talk about ethics. There are many ethical decisions, and whenever I talk about self-driving, someone asks me about the trolley problem. Okay? So don't ask me about the trolley problem. No, just kidding, you can ask. Okay? But the trolley problem is an ethical question, but it's not really interesting and useful and practical ethical questions. It's an ethical question for philosopher. It's not a practical ethical question. The practical ethical question is striking the right balance between usefulness of the driving of the road system and safety. And this is an ethical question. If you will put the speed limit to 10 kilometers per hour, then the roads will be safer, but they will not be efficient. And as a society, we need to make an ethical decision of how much we are balancing usefulness and safety. In the same way, when we give vaccines, we are asking these questions, and when we are doing insurance, we are asking these questions. And these are the real ethical questions. How to formalize what is called the vague term of the duty of care, the responsibility to not cause harm. We need to make the right balance between not making harm, but living. So I will skip the details, and I will go on in the 5 minutes that left to talk about the more general problem of the AI alignment problem. So what we saw in self-driving car, that we could come up with a safety net with mathematical guarantees that protect us against the dangers of malbehavior of AI systems and machine learning algorithms, deep learning algorithms. So we want the machine learning and deep learning algorithms, but we also want something more. We want a safety net that will protect us if they are misbehaving. And the question is, can we do something similar for the more general AI alignment problem? So let me explain what is the AI alignment problem. I like to explain it based on the famous story about Mickey Mouse in the Fantasy 2000 movie that needed to fill the cauldron. Okay? He was the assistant of the sorcerer, and he got the task of filling the cauldron with water, and he was lazy, he didn't want, so he wanted to build a humanoid robot that will do it for him. But instead, he just cast a spell on the broom and commanded the broom to fill the cauldron. The problem is that the broom started to fill more and more and more and more waters and never stop, and everything was flooded. Okay? So this is the alignment problem. We want to build the AI to fill a cauldron and give it a reward of 1 if it is full and 0 if it is not full. Sounds good? Sounds reasonable? But this is not what we really want. We don't care if it is 99.9% full or 100% full. And why does it matter? Because if the reward is only when it is 100% full, then because some water will vaporize, then you want to just fill more and more water so that it will be really full. And you never told the models that you don't want that everything will be flooded. Okay, you forgot to mention it to the model. And you forgot to mention to the model that you don't really care about 100% or 99.9%. So in retrospect, it's obvious. But the question, we might do this error, okay, and then find out later that we are in a big problem. So the first idea that comes to mind is let's have a red button of stop, okay? So if we can always stop the AI, then we are fine. But it's not that easy, because the stop button can be an obstacle to the reward of the AI. So the AI might decide to prevent you from stopping it. Okay, so let's add reward for pressing the stop button. Then the AI will manipulate you to press it. So let's not allowing the AI to push it. Yeah, it will manipulate you, and you can go around it. And the bottom line is that the red button problem is unsolvable for AI which is smarter than you. Okay, because it will always be able to manipulate you to do what it really needs. Okay, so are we scared? Still, many AI researchers are not scared. Why? Because it's too early, we are still far away from artificial general intelligence, or because since we designed it, we understand enough to make it safe. But the example here is an example that it can happen today with today's technology, the alignment problem. So say, for example, you say, I want to train self-driving cars, and the reward is safety, no accidents, comfort, and usefulness. We want to drive as fast as possible up to the speed limit. Sounds good, but then all the fleet of cars can decide to suddenly stop. All the humans will get confused, will go out, then locking the doors and driving at the speed limit all the cars. So we forgot something. We also want human to use a service. So the reward looked okay, but it's actually not. So are you scared? So the thing is that all innovation is dangerous. And what we want to make is a distinction between strategic alignment problem and agnostic alignment problem. When we invented the combustion engine, we didn't think about the climate change. Okay? But this is not a strategic problem with this combustion engine. It's a butterfly effect. And this is unavoidable. All progress can come with some side effects. And we will deal with it when they will come. Or not. But this is not something unique for AI. The danger in AI is strategic alignment is what happens if the AI, for optimizing exactly its reward, will strategically manipulate and change the distribution of the word so as to succeed. This is more dangerous. And my time is up, but maybe one more minute. Can I continue? Okay. So my point is that we can and we should prevent strategic AI alignment. And we wrote a paper how to do it. And again, we talked about the distinction between learning from data and learning from experience. Learning from data is fine. Learning from experience is where the problem arises. It can suffer from strategic AI alignment, but we can protect it by having some machineries. I don't have time to explain all the details. I'll just tell you that we almost solved the problem. So we can solve the strategic AI alignment problem unless we are suffering from the matrix problem. And what is a matrix problem? It's not the mathematical matrix, it's a moving the matrix. And the issue is that we might think all is good, but it's not, like all the people that are living inside the matrix. And for that, we don't have really a solution. But I think that an important and interesting point to make, and it's a good point to stop my talk. So thank you very much for listening.